Okay, in our first question here, we have a 400 Newton object. We're told that it's hanging from two ropes. One rope is attached to the ceiling and makes an angle of 40 degrees with the ceiling. The other rope is attached to the wall and makes an angle of 50 degrees with the wall. We want to calculate the tension in the two ropes. So the first thing we want to do is we want to take this information that they've given us in terms of angles and forces and represent it all in a diagram. So we know that we have a ceiling and we have a wall. And we'll sort of fill in the ceiling a little bit and fill in the wall a bit so that we know that these are not parts of our diagram. These are sort of parts of the physical space around it. So we've got some object here, and we know that it is hanging from two ropes. So we'll sort of draw a rope like this, which is attached to the ceiling, and it's got another rope which is attached to the wall. So this thing is sort of suspended here like this. And what are we told about these ropes? Well, we're told that one of them makes an angle of 40 degrees with the ceiling. So that's got to be 40 degrees in here. And the other rope is attached to the wall, makes an angle of 50 degrees with the wall. So that's got to be that angle right in there. And what we're interested in is the tension in the two ropes. So what's happening in this situation here is the mass of our object here is pulling down. This is sort of the force of gravity due to this object. And we're told what that force is, 400 newtons. So that's giving us the weight or the gravitational force that this object exerts. But because this object isn't going anywhere, it's in what we call equilibrium, there has to be forces that are keeping it in one spot. And the forces that are keeping it sort of stationary are coming from these two ropes here. And we call these forces the tension in the ropes. So we've got one force here, which is sort of pulling up on an angle like that, and another force over here, which is again pulling up like that. So these two are sort of pulling up and out and keeping this object from going anywhere. So we're going to call these two forces, or these two tensions, tension 1 and tension 2, for want of a better word. Okay. And because nothing's moving in this picture, this thing is just hanging here, we know that all of these forces are in equilibrium. So if we add them all up, they have to add to 0 because there's no what they call unbalanced force on this object. So tension 1 plus tension 2 plus the force of gravity all have to add up to 0. And this is vector addition that we're doing here. We're adding these three vectors. And we should make a little note here because this is in equilibrium. And you know it's in equilibrium because nothing is moving anywhere. Now to simplify this a little bit, what we can say is that I can bring this gravitational force to the other side of the equation. Then I get T1 plus T2 equals negative Fg. So we've drawn ourselves a picture of the given information, and we've come up with sort of an idea of how these vectors have to be added together. The next step is to take what we've drawn in this diagram and turn it into a vector diagram where we show this addition taking place, where we add the vector representing T1 to the vector representing T2 and get them to equal the opposite of our force vector. So let's do that here. Let's take T1, which is a vector that looks like this, T2, which is a vector that looks like this, so T1, T2, we add these together, and we're going to get the opposite of Fg. So same vector with the same magnitude, just pointing in the opposite direction. So instead of pointing down, it's going to point up. And I've drawn these so that T1 plus T2, I put them tip to tail, so we're adding them up. And when we add them up, we get the opposite of our gravitational force. And then we want to transfer our information about magnitudes and directions over to this new diagram. So we know that the magnitude of negative Fg is 400, and we don't know the magnitudes of either T1 or T2, but we do have some information about their angles here. So what I like to do in this picture over here is take these little things, these little crosses here, and I put them at my vertices. Okay? So it can help me to sort of help me organize the angle information. So start with T1 here. The angle between the tip of T1 and the horizontal, this angle right here, is 40 degrees. So if we go to T1, we go to the tip, and we go up to the horizontal, that has to be 40 degrees in there. Not all the way up to T2, but just up to the horizontal. And let's see, what do we have for T2? We've got a 50-degree angle over here, and that's between the tip of T2 and the vertical. So between the tip of T2 and the vertical, right in here, has to be 50 degrees. Now, is there anything else that we can add in here? Well, let's see. If I extend this across like this, this has got to be 90 degrees and 90 degrees because that gravitational force is straight vertical. So if this is 50 degrees in here, I've got a little right angle triangle. This one in here has to be 40 degrees as well. 40 and 50 give us 90, and another 90 give us 180. I can do the same thing for this other triangle down below. I've got 40 there, 90 there. So this has got to be 50 down there. So now I've filled in all my angles. What do I want to calculate? Well, I want to calculate the tension in the two ropes. So really all I need is the magnitude of T1 and the magnitude of T2. How can I get these magnitudes? Well, I know all the angles of my triangles. I know the magnitude or the length of one side, so I can use sine law here. The magnitude of T1, or the length of this side, divided by the sine of the angle opposite, so sine 50 degrees, is going to equal, I know this side over here, 400, and I know the sine of the, I know the angle opposite is going to be 80 degrees. So sine 80 degrees. And then I can just solve this using the sine law. The magnitude of T1, I do 400 times sine 50 degrees, divide by the sine of 80 degrees, and I get 311 point 14 newtons. And that's not much of an N. Okay? So that is the tension in one of my ropes. Now when they ask for tension, you only ever have to give the magnitude of this force because the direction is sort of assumed to be wherever the rope is pointing. Okay? And now we need the tension in the second rope here. So let's see. We can do the same thing. Sine law, T2. We're also going to use that 400 divided by sine 80 degrees. That's the side angle pair that we were given in the question. And what's the angle that is opposite T2? Oh, that's also 50 degrees. So it turns out here that our two tensions are going to be exactly the same. The magnitude of T2 is also 311.14 newtons. So those two tensions, the magnitudes of those two forces, is our final answer.